Hello everyone, welcome to this video on Statistical Process Control, and this video is an introduction to Statistical Process Control, specifically an introduction to run charts and control charts. So what Statistical Process Control is certain companies, businesses, manufacturers, whatever, have many processes that run throughout a day or throughout, over long periods of time that depend on human resources, equipment, budgeting, all sorts of things. There's certain methods and procedures that are in place to create an object or a good or a service. And what we do in statistical process control is kind of keep track of data for a certain process over over a certain span of time, and then analyze that data. All right, we look at the data over a certain period of time and determine, is this data happening naturally, occurring in a naturally random way, or is there some sort of unnatural occurrence in the data, which would suggest that the process is out of control. There's something that needs to be fixed, perhaps. The way I make the good, the way I service the product, the way I maybe my manufacturing tools need to be tweaked a bit, need to be repaired, or and so on. So that's what we're doing in statistical process control, is looking at a process over some period of time and seeing if we can see possible errors in the data, reasons that the process that we're looking at may be in or out of control. All right. So statistical process control. This video is going to be just, it's an introduction. So there's a lot of definitions. So please bear with me. And then we'll, in the future videos after this, I'll get into some examples where we look at more data and actually perform statistical process controlling, all right, or quality controlling. So the first definition I have here is process data. Process data are data arranged according to some time sequence, right? So like I mentioned, we're going to be recording data generated from a certain procedure, a certain process over time. They are measurements of a characteristic of goods or services that result from some combination of equipment, people, materials, methods, and conditions. So we're going to be measuring a certain characteristic of manufactured goods or a service that we're performing over a length of time. Now this characteristic could be the mean value of some samples of data. We'll see that we'll record how about the variation in the data, some samples of data over time, or just proportions of some characteristic over time. You're going to see examples of charts like these coming up. And what we're going to do is take this data and create a chart from this data, a time chart. Now the first kind of chart is this where we record every individual piece of data. That's a run chart. Right, a run chart is a sequential plot of individual data values over time. So they'll look something like this. Now I've drawn this one out by hand. I've got an example coming up later in the video where I have a piece of technology. Actually, I'm using Google Sheets. You could use Excel, Google Sheets, Minitab, SPSS, lots of StatCrunch, lots of statistical software out there. Your calculator and a TI-84 or 85. But the thing is, we're going to be working with probably large sets of data that would be tedious, to say the least, to put into a calculator of the TI-83 or 84 nature. So they'll look like this: a run chart. Got my two axes. Typically along the horizontal axis will be some sort of time units. So there'd be 1 day, 2 days, third day, fourth day, or hours, or minutes, or whatever. All right, so I have an axis of time units, typically the horizontal axis, and the vertical axis is this measurement of the characteristic, these possible values of that characteristic that's being measured, and represented by the vertical axis. And so on day one, we record a value of bleh. And then on day two, or time two, we record a value of bleh. And I mark off points, right? Just plot points. And they're typically connected by little segments just to kind of make it easier to see which way things are trending. And very often in a run chart, not always, but later when we talk about control charts, these will always be here. There's this dotted line or a line drawn through the data that's at the center line, which will be, this line will be at the mean value of the data, the average value, mean value. Again, for my example today, I don't have this, but when we get into videos later on things called control charts for certain characteristics, then I will have this center line drawn in along with upper limit and lower limit lines, which I'll get into later. But again, a run chart, pretty easy to make, or have a piece of technology make it for you. And I'm not going to get into that, how to have Excel or Google Sheets or Minitab or anything like that. I'm not going to get into that in this video. The point is just to introduce you to this stuff and show you some pictures, right? Read you some definitions and show you some pictures. All right, and then what we're gonna do is take a look at these charts, either a run chart or later a control chart, and determine whether or not our process, right, the process that we're studying, is in statistical control or statistically stable. All right, so we're going to take a look at these run charts, and like I said later, control charts, and we're going to determine if a process, right, the process that we're studying, collecting data on, is that process statistically stable or within statistical control. And here's what this means. A process is statistically stable or within statistical control if it has only natural variation. Right, it's like naturally random, with no patterns, no cycles, no unusual points, right? I don't want to see in my run chart or a control chart, I don't want to see patterns, cycles, unusual points, meaning very high points or very low points compared to the rest of the data. Because basically I don't want to see stuff that wouldn't naturally occur, right? Patterns do not occur naturally, right? You go out and look at stones, right? Stones don't form triangles, perfect triangles, perfect squares. You don't see perfect patterns or cycles in nature. Now, yes, there are things that follow patterns in nature, sure, but you don't see perfect patterns, perfect cycles occurring naturally. Right? If something's has natural variation or naturally random. All right, and you'll see more what I mean when I get into some examples of what we're looking for that would be considered unnatural. So in our run charts, a run chart with no obvious pattern, right? Something we can't see an obvious pattern formed by the points, suggests that the data are from a process that is statistically stable. Right? So it would suggest to us that the process is running well and there is no need to fix it. Unless some manufacturing specifications aren't met, but that's up to a particular manufacturer or a particular company, right? But a company's specifications change from time to time. So a process may work well, but if all of a sudden the specifications from the company are changed, then the process would have to be fixed. But if specifications aren't changed and we're seeing a run chart with no obvious pattern, that would suggest to us that the data are from a process that is stable, that is in control, and we wouldn't need to do any tweaking to that process because it seems like it's working naturally well. All right. So now some examples, some pictures here. What do I mean by no obvious pattern, or when are we going to determine that a run chart that for a process? When are we going to determine that a process is or is not statistically stable? Right. So how do we interpret run charts when we're looking at them? Right. So interpreting run charts. So violating one or more of the following criteria would indicate that a process is not statistically stable or is out of statistical control, and then there's something wrong. There's seemingly something wrong with the process, and we should go in and tweak some things and figure out where things are going wrong. Is it with the people? Is it with the machines? Is it with the process, the steps of the process itself? And go in and try to fix things, and then re-record data, look at another chart over some period of time, and see if the fix was made. Sorry, this segment shouldn't be here. Okay. So 1, if you're noticing increasing variation in the data. So an example is something like that, a run chart where that happens. See, so again, data values in the vertical, time on the horizontal. If the data points seem to spread further apart over time, that's not good, right? The variation increases. Then you'll eventually get some data values that are way too big or way too small for what our desired specifications are, and the process is out of whack, is out of control in that case. Right? And maybe you can see it happening in my example here. If I had a run chart that looked like this, you see how that doesn't vary all that much, right? The width between high and low in the beginning is pretty small, but then it spreads very much as we go along, right? At the end here, the variation is much larger. And if this were to continue, right, if I didn't step in as a company manager, if I didn't step in and fix this process, whatever it is, again, be it maybe it's a manufacturing process where a good example would be like bottling companies for like places that sell sodas or manufacture soda cans, soda bottles. If each this bottle's filled, if I want my bottles to be filled with 32 ounces or something, right? Say 32 ounces is the specification, and maybe all these guys in the beginning, all these bottles are filled with reasonable amounts around 32 ounces, right? It might not be perfect every single time, but then over time, some bottles are getting overfilled, some bottles are getting underfilled way too much, and I would say to myself, hey, this isn't looking so hot. I better go in and probably either tweak the machines or figure out who's running them and see what maybe they're doing something wrong. Try to figure out how to fix the problem before it gets way too out of hand. All right, so if you're seeing increasing variation in a run chart or a control chart that we'll talk about later, we would most likely say, hey, this particular process is out of control or is not statistically stable. All right, so then some other ones, some other things to look out for. Number 2, if there's an obvious upward trend in the data. So an example here in data versus time, right? My data values, they're bouncing up and down and whatnot, but you see how they are definitely tending on an upward slope, definitely tending to increase as time passes. So again, just to stick with the bottling example, if I wanted to have around 32 ounces, have a machine fill every bottle with around 32 ounces, and I take some samples every day, and I take a bottle every hour, every 10 minutes or so, and see how much the machine's bottling. maybe down here it's starting off around 32, give or take a milliliter or something. It's starting off around the correct amount, but then it's like it keeps bumping up 0.1 milliliter, zero point 0.1 milliliter, whatever. It keeps. I notice over time as I take more and more bottles out and record how much they're filled, I notice, hey, this is getting out of control, right? I'm filling these the machine is starting to fill these bottles way too much, and I'll be losing profit and whatnot, and something is up with these machines, or again the people running them, or something. I gotta go. I would look at something like this and say something is wrong. This process of the bottle filling is not statistically stable. It's out of control. I gotta fix something, and then figure out where the problem is and go from there. Make decisions. Same thing for a downward trend. Right, if you're noticing in a run chart that my data values are tending to decrease over time, yeah, there's some parts where it bumps up and down with my, again, using the bottle example. If I just take, oh, these bottles seem to be around the correct amount of filling, but then, oh, these are lower, and then these are lower, and then these are lower, these are lower. This is a bad trend, right? It's like, ooh, I'm underfilling these bottles now, right? Consistently. So I'm noticing this data tending to decrease as time passes. Then this is where I'm cheating the customer. Like they expect 32 ounces, around 32 ounces to be in this bottle, but over time I'm noticing my machines are not filling these bottles with the correct amount. They're tending to underfill the bottle. So something's wrong. Something seems out of control in this bottling process. So then I'd try to go in and figure out what's wrong. Right? Is it the machine? I would most likely again check the machines, make sure they're operating correctly, or whoever is running them, make sure that they're doing their job correctly and stuff like that, and fix the issue, and then start over and run another runs chart. Maybe taking a bottle every 10 minutes and recording it's how filled it is, and seeing another run chart and seeing if the process has gone back under control. All right. So again, patterns, right? We don't want to see any particular unnatural pattern showing up in a chart, or the process we're looking at is most likely out of control or not stable. Number 4, another pattern that would be problematic, pardon me, if there were some sort of sudden upward shift in points. Right, so again, an example here, I'm not using any values as you've noticed, but data points all down here, down here, down here, and then there's a shift, and then all of a sudden all the data points are suddenly around here, up much higher. So you see all these data points in the beginning have a low average or a lower average, and then the data points at the end have a much higher average, telling me that something shifted in the process. Something occurred in this process that threw it out of whack. All right, threw it out of control. All right, so if points at the end tend to be significantly higher than points at the beginning, you can justify saying that your process is statistically unstable or statistically out of control, and then you say, hey, there's a problem here. I should go in and try to figure out what the problem is and try to fix it. Same thing for a downward shift, right? If you had, and this is just one example of a picture like this, where again the points in the beginning, all the data values in the beginning are around the same value, right? Have a pretty high average or around the same average, and then all of a sudden that dips, and then all the points later in the process, later in the recordings, have a much lower average than they did in the first parts of the recordings. So again, something shifted in the process, something got broken, something needs to be fixed. It's out of control, it's unstable. Again, with the bottling example, right? Hey, maybe I notice, hey, all right, all these bottles here are filled about the same amount. Looks like the process is good so far. Things are working the way I wish, and then wait, whoa, what happened? All these bottles down here are being underfilled. Something went wrong with the machines. Something, and again, this example with the bottling is just one example. You could apply this to almost any manufacturing process, any goods or service process. whether it be like wait times at a McDonald's. You could in a McDonald's drive-through or something. You know, hey, all these customers here had around the same wait times in the drive-through, and then all of a sudden, all these customers had much lower wait times. Now that's a good thing, all right? That's a great thing if you're talking about wait times, but still something happened, right? You can see that something happened in this process, and you might want to figure out what that was. So that way, you figure out, oh, certain people were working at these times, certain people were working at these times, and have some sort of performance review where you tell, hey, you people on this job, on this shift, you need to get your act together so that we can be more stable. All right. Again, bottling, manufacturing, goods and services. You can apply this to a lot of things in business and real world applications. Another thing to look out for. Again, notice patterns, right? When you see obvious patterns appearing, something's up, right? There's not statistical stability, and you have to try to fix something. Exceptional values are another thing to look out for. Exceptionally high or exceptionally low. And we'll see this much more clearly when we talk about control charts later. Because in a control chart, there's something called an upper control limit and a lower control limit. That if I'm higher than the upper control limit, it's too high, and if I'm lower than the lower control limit, it's too low. So say I had some data here again. I was bottling, again, checking my bottling, right, bottling some Coke bottles or something. All these seem to be being filled around the same amount. But then all of a sudden, this one bottle I chose was way overfilled, and then these other ones were back to normal. That exceptionally high point tells me, hey, what happened? Something happened in this process that I would like to take care of now before it becomes too much of a problem. All right? You don't ignore something like this in a run chart, a data chart like this. I see this exceptionally high value, say, hey, okay, I mean, things looked good for a while and look good on average, but I don't want this to happen again, right? So I got to go back in and see, what time was that at? Maybe who was working at that time, or was there a power surge or a power outage at the company, or was there what kind of factors came into play to cause that giant spike? And how can I repair it, and how can I fix it so it doesn't happen again? Same thing for an exceptionally low value, right? If I had a run chart like this where all these bottles are being filled about the same amount, great. But then all of a sudden I found one, I pulled one off the line and it was way underfilled. And then the other ones I pulled off the line later were about the same. It's like, hey, what caused this? Right? What caused this exceptionally low point? I don't like this. I don't want this to happen again. So I'd say this process wasn't in control, right, fully. Looks pretty good up here, for these bottles I chose, but I'd say the process of this bottling wasn't in control fully, and I would go back in and see what time was this at, what factors caused this very low point to occur, and try to fix those points. Try to fix the process so that doesn't happen again. All right, then one more. Again, all these have about the same theme, right? Have the same theme. If it doesn't seem like there's some natural randomness going on, something's happening, right? The process isn't in control. It's something in it is biased. Something in it is occurring that I don't want to keep occurring. Right? And so far everything I mentioned is you're just looking for patterns. Cyclical patterns, right? Things repeating in cycles aren't natural, right? Obvious patterns to the data aren't natural. Perfect patterns are not naturally occurring things. So if there's perfect patterns or nice obvious patterns appearing in your data, there is a good chance that something's wrong with that process. Something is fixing it so that that cycle keeps occurring. and you have to go in and figure out why that is. Why does this cycle keep occurring? What can I do to fix it? All right. So, so any cyclical pattern or obvious pattern like this one here, something like this, where it's the data values are coming in up, low, high, low, high, low, high, low, high, low, high. I mean, I know they're probably, you might think, hey, they're all around the same. That's great, but there's no way this would happen naturally. It's underfilled and overfilled and underfilled and overfilled and underfilled and overfilled, underfilled, overfilled, underfilled, overfilled, underfilled, overfilled, underfilled, overfilled, underfilled. Right? There's no way that would happen naturally. Right? You wouldn't expect that to happen randomly. It's like flipping a coin. Right? You wouldn't expect heads and tails and heads and tails and heads and tails, right? You wouldn't expect that to happen, and that shouldn't happen naturally. So if I see something like this that has an obvious, say up-down pattern like this, something's up with my machines, something's up with my process, and I need to go in and figure out what that is. I need to figure out what's wrong with the machines, what's wrong with the people working the machines, and how do I remedy the situation so that I get more naturally occurring results. And again, I just have a couple examples here. There's obviously, other patterns that could show up, but maybe it's like, hey, what if I see this like wave pattern going on here with all the data points? Again, something like this wouldn't happen naturally. Something must be up with the machines, something must be up with my employees, something must be up with the steps of the process itself to make this particular fixed pattern, this wave pattern occur. And I need to go in and figure out what that is before it's too late, because if a particular pattern holds, then someone could easily come in and figure out how to screw with me, right, and mess with my stuff at the right times because they see it happening in a pattern too, right? All right, and of course, and more, right? There's obviously more perfect patterns out there that could occur in your data. Maybe they form a parabola shape, or a perfect line, or something that's not going to occur naturally. All right, so if I look through, now again, these are just 7 criteria, 7 conditions I'm looking out for. If these 7 things don't happen, if I don't notice that there's super high values, super low values, I don't notice any particular pattern, or it's not always trending upward, not always trending downward, there's no major shift in the data, then I will deem the process within control or statistically stable. All right. So I just have one example of this. Again, so I have an example. It says example 1. There's no example 2. Right. So see the chart referring to axial loads of aluminum cans that are, say 0.0109 inches thick. There were 7 measurements taken each day for a total of 25 days. So that's a total of 175 measurements. All right, so we're talking about, aluminum cans. Right, and the thickness of the cans, right? If you talk about the thickness of the sides, the thickness of these cans is 0.0109 inches, very thin, right? And then axial load is the lids. Right, here's the lid of the can. Lids are like forced down by a machine. Right, lids are pressed in by a machine, and the axial load is the weight that's needed, or the force that's needed to press the lid onto the can, right? So if the weight, if the weight's too, if the weight's too high, the can will get crushed. If it's too low, the lid won't stay on securely. All right. So there's got to be some some preferred axial load. There's got to be a certain weight of force with a certain tolerance, right? Because again, a machine's not going to be perfectly doing it every single time. It's there's always some itty bitty tolerance on either side. Either too much or too high at any given press. But there are some specifications as to what the perfect axial load is, you program the machine to do that, and then hopefully it stays consistent. All right, and let's see if our measurements here are consistent. Now I have, I'm going to go to my Google Sheets page where I have 175 of these measurements, these axial loads measurements on some cans. All right, some cans that what's their maximum axial load, right? So the maximum amount of weight that they can take before being crushed, right, when pressing the lids on. So let me show you what I've got. All right, so here it says cans, it says cans 109, that's the 0.0109 inches thick, and I have 175 measurements here. All right, ignore the second column, the column C, that's just the number, number 55, number 56, number 57. Just look at column B. All right, so you see 175 of these. I know it says 176, but the top row said cans 109. So like this last can that I measured on the last day, had a maximum axial load of 292, meaning it would take up to, it took up to 292 pounds to crush it, right, before it couldn't take the pressing of the lid anymore. Then 274 for this can, 290 for this can, 293 for this can, 262 pounds for that can, and so on. Right, and as I mentioned on my writing, on the written page, there were 7 measurements taken each day for a total of 25 days, right, making the total of 175 measurements. All right, let's look at the run chart for this. All right, so here it is. Here's the run chart for axial load of cans that are 0.0109 inches thick. You see my vertical numbers here represent the maximum axial load in pounds, right? The maximum amount of force that these cans could take that I sampled before they got crushed. And then the cans in order of the time sampled, so can 1 up to can 175, right? All 175 cans in the order that I took them, right? So that's over some time, right? Usually the horizontal axis will represent some sort of time measurement. So again, these dots represent each cans. It just represent every point in this column with starting with 270, 273, 258, 204, 254, 228, and so on. And there is an example of a run chart with 175 different points, right, at 175 different periods of time. Where the first 7 of these were taken in the first day, and the next 7 were in the second day, and the last 7 points on the right side of the chart, the last 7 were taken on the 25th day. All right, so let's look at this run chart here and interpret it. Do I have, going through my little criteria, like looking for patterns and whatnot, is this procedure of, is this machine that's placing lids on my cans, is it in control? Is it stable? Or is something wrong with it? Or just this process of the pressing on of lids. Is the process of pressing on of lids stable? Is it in control? Or is there something I feel like I need to fix? Now, you notice how none of these are much. Let's look at, is there increasing variation? Number 1, is there increasing variation? So you see on the left, well, they're all between this 200 and 300 band, aren't they? Every single one of these pairs. Now, in fact, I'd say it's getting smaller, the variation, right? See how over here it starts off, almost to 300, then down here almost to 200, so about a range of almost 100. But then at the end, the range is smaller, so there's not an increase in variation, which would be bad, right? An increase in variation tells me, oh, things are getting out of control. I don't want things to get too far apart. I want things to be more and more consistent. So it looks like this machine that's pressing on can lids here is actually getting better for somehow, all right, or staying more consistent at least, all right. Okay, so I'm not seeing, number 1, I'm not seeing increased variation. Is there an upward trend? I mean, does it look like my page here, right? Does it look like it's definitely, tending upward the whole time? The values are increasing for certain. The values on the right are much, much higher than the values on the left. That doesn't seem to be happening either, right? I mean, sure, again, there's values over here on the left side that are about the same as the values on the right side, so it doesn't look like it's trending upward. It also doesn't look like it's trending downward for that same reason, right? The values that in the beginning are about the same as, right? The values in the beginning are about the same as the values at the end, right? So I'm not seeing some upward trend. I'm not seeing some downward trend, right? Seeming about level the whole way through. Is there, again, is there an upward shift, right? Going back to my pictures. Remember, upward shift means, the beginning values start around the same level, and then there's this, like, all of a sudden an upward shift in the data, and then my values on the right half or the latter part of the data seem to be much higher. Or a downward shift in a very similar fashion. Is that happening? Doesn't look like it. Doesn't look like it. I mean, all these points are around the same level as these points. I mean, they're a little higher, I guess, on average, but there's still some points in the beginning here that are about the same level as these points at the end. So I'm not seeing a major upward shift. I'm not seeing a major downward shift in this data. Okay. Are there any... Now, we don't have upper control limits defined here or lower control limits defined, upper limits and lower limits, as I've mentioned. So the talk about exceptional values, unless it's super obvious that there's a value way far away from the other ones on average, or a value way below the other ones on average, we're just going to look at a run chart and say, oh, they all seem about grouped together. Like I mentioned, they all seem about between this 200 and 300 band. Right? There's not a value way down here. There's not a value way up here. Right? All of these values I'm seeing are, now I know there's these peaks, these little sharp points with values around 200, but there's multiples of them. I mean, there's large group. Every single bunch of these is between 200 and 300. So again, I'm not seeing anything that's exceptionally low, or above, way above 300, exceptionally high. And again, without specified upper limit and lower limit, I would not say that any of these are too high or too low. Right? Again, they're all around the same band. Okay, so far so good. So far this is looking like, the process of putting lids on these cans, the process of pressing lids onto these cans for me, for this company, seems to be within control so far. And then the last part, is there some obvious pattern here to you? That is there some cyclical pattern or some obvious pattern? Right, like I mentioned here, is it up down up down up down up down, or some wave pattern, or some sawtooth pattern like the up down, or is it a perfectly straight line, or like a parabola, or close to an exponential, or close to some other kind of function? Again, I'm not in this run chart here, not really seeing a pattern where I could figure out, like, hey, if I did this 100, if I did this 10 more times, if I took 10 more, if I took 10 more cans tomorrow, I couldn't predict really where those cans maximum axial loads would be, right? Because I'm not seeing a pattern here. I'm not seeing something that I could predict the future with, and that's good, right? You shouldn't naturally be able to predict the future of your process, right? If it's in control, right? If it's out of control, you'd like to change the future, sure. But I'm not, again, I'm not seeing some obvious pattern here. So for this particular run chart, all those conditions that would cause me to say it was out of control are not happening. So back on my page with the writing, right? So based on the chart, right, based on the run chart, I would say this process of pressing lids onto cans right, as it pertains to axial load. The things I was measuring. This process of pressing lids onto cans as it pertains to axial load is statistically stable. It is stable. It is in control. So I would say, hey, leave the machines alone. They seem to be doing their job reasonably well. There's nothing really I need to take care of here, nothing I need to fix. All right. And that's how I would, if I was asked, a question about this, asked to look at a run chart for that data and ask if the process in which that data was collected was stable or not, I would say it was stable. As again, one more time, it wasn't there wasn't increasing variation, right? It wasn't spreading out and getting wider and wider as time went on. It wasn't tending to increase. It wasn't tending to decrease the data. There was no major upward shift. There was no major downward shift. There weren't exceptional values, either super high or super low compared to the rest of them. And again, I wasn't seeing, to me anyway, if you see something, hey, maybe you can argue it, but I'm not seeing any very obvious pattern in this data. So I would say the process, again, of pressing lids onto these cans as it pertains to these axial load measurements is stable, is in control. Okay. All right. So now, right, that was an example involving a run chart where I, labeled every individual can, right? In a run chart, you're labeling every individual piece of data, right? But very often, instead of doing that, because that can be a bit tedious, a bit time consuming, and maybe not give you as much information as you need, or too much information, very often, instead of looking at a run chart where every individual piece of data is recorded, we look at a control chart where we look at groups of data and then one particular aspect of those groups and plot that over time. All right, so it's very similar to run chart, right? Very similar to run chart. So control charts. And again, this is just an introduction to control charts. I'm not going to do any examples. The videos I have after this are going to be on different types of control charts. A control chart, or Shewhart chart, named after Walter Shewhart, who first introduced these in 1924. If you'd like to look him up, Walter Shewhart. Interesting read, or read a Wikipedia article about him or something. A control chart, or Shewhart chart, I'll just probably use control chart. A control chart of a process characteristic, right? So again, we're such as a mean or a variation. All right, so instead of, like I said, instead of recording each individual piece of data, we're going to look at groups of data and then see how the groups of data, how one characteristic of those groups changes over time. So how do the means change over time? Or how do the variances or ranges change over time, or the proportion of some attribute change over time? All right, so that's the major difference between control chart and run chart. Run chart, again, every individual piece of data. Control chart, you're grabbing groups of data and looking at one particular characteristic and seeing how that particular characteristic changes from group to group over time. And again, if you don't understand what I just said, see my future videos coming out after this on different types of control charts when they're done. All right, so these control charts of a control chart of a process characteristic, such as a mean or variation, consists of values plotted sequentially over time, just like a run chart, very similar. All right, the major difference is you're going to see these three lines show up on a control chart, and I'll show you what these are. So you have vertical axis, horizontal axis. Again, the horizontal axis will represent time in so many units, 1 day, 2 days, 3 days, 1 hour, 2 hour, 3 hours, seconds, minutes, whatever. And the vertical axis represent these values of the characteristic. All right, and I should actually say characteristic values. Possible characteristic values. Means, ranges, proportions, whatever we're recording about these groups of data we're gathering. So like my examples with bottling earlier, right? That the bottling Coke cans, instead of recording how much one can is filled, maybe I want to record the means of groups of cans, right? So every day I grab 10 cans and find the average or the mean amount they're filled and record that, and that becomes, one day's recording. Then the next day I grab 10 more cans and find the mean of how much they're filled and record that. And then the third day I do the same, 10 more cans. The fourth day, 10 more cans. So it's a way to consolidate data, right? Because over 3 days I'd only have 3 points instead of 30, right? Instead of one for each individual can. I just have a point that kind of represents that day, or the average of that day, or the range of that day, or what proportion of those cans was above the specification I wanted, or what proportion of those cans was below the specification that I wanted. Right, so this is actually a way to condense data. It's like a condensed run chart. All right, then on a control chart, you're going to see 3 lines, and I write them as dashed lines. They could be solid, it doesn't matter. One line running through basically like the heart of the data, the center line, which will have the mean value of all the data points. Right? So whatever the mean of all these data points is, that's where the center line is going to go at that value. And then there are these there's a value upper control limit, or UCL, and lower control limit, LCL, that are going to be on the chart. And these upper control limit and lower control limits will indicate to us, remember I mentioned exceptionally high or exceptionally low values earlier. If a value ends up above the upper control limit, it's going to be considered exceptionally high, or significantly high. Right? And if a value ends up being up here, right, above our upper control limit, then we'll say the process being recorded, the process being studied, is out of control or not stable. And same thing for the lower control limit, or LCL. If any data points show up below this line, then we'll consider that piece of data exceptionally low or significantly low. And if we did have a data point that ended up down here, then I would say this process I'm looking at, right, is statistically unstable, is out of control. Something's wrong somewhere. I got to go in and fix it. Now that doesn't mean if you are all between these that you're fine, right? Remember, there's still a bunch of other things to look out for, right? Is it always increasing? Is it always decreasing? Is there that shift up or that shift down, or is there some obvious pattern, right? So just because there aren't points above and below this doesn't mean that it's in control. Right? Now these limits, as you'll see in videos after this, I'm not going to do it in this video. These upper control limit and lower control limit, these are typically found with a table or some simple calculation, which again I'll show you when we go into videos on different types of control charts, right, where we're gonna try to look at the process, a different process characteristic. All right, so every control chart is going to look something like this. And here are some examples of control charts that I'll be making videos on after this. One control chart is for looking at a process and monitoring the variation in samples throughout that process, referred to as an R chart. R for range. All right, range chart. Let me put that next to it. R for range. All right, so what happens in this is like for instance, again, the bottling example, I, for the, maybe on the first day, I take, 20 bottles and find how much they're filled, and then find the range, right? The highest amount minus the lowest amount. And I simply record that range, and that's it, right? So this one dot represents 20 bottles, the range of 20 bottles. Then I do the same thing for the second day. I take another 20 bottles and find their range and record that. And then the third day, take another 20 bottles, find their range and record that, and so on. That would be an R chart. Right? We're monitoring the range, we're monitoring the variation in the data. Then for monitoring, there's another control chart for where we just simply monitor the means of the data. Right? So again, like I was saying earlier, first day I take 20 bottles and find their mean, the mean of how much they're filled. Next day I take a group of bottles, find their mean. Next day I take a group of bottles and find their mean, and so on. All right. This is called an X bar chart. Remember, X bar was usually used for sample mean, right? This is a mean chart and monitoring means. Right. And then lastly, a control chart where I look at a process and monitor attributes, or a P chart, right? A proportion chart. P, remember, P was usually used for a sample proportion or a population proportion, some sort of proportion. That's right, proportions. So I pick an attribute, usually in manufacturing, an attribute would be, defective or not defective. Is this product defective or not? So say I'm manufacturing a bunch of like car radios, right? And on the first day, I take 30 car radios from my plant, and I say what proportion, what percentage of those radios are defective, and I record that for day one. Then for the next day, same thing. I take another 30 car radios I produced, determine what percentage, what proportion of those are defective, and record that. And do the same thing the next day, the next day, the next day, and that would create for me a P chart. And then we'll look at that P chart and determine if this manufacturing process is in statistical control or not. All right. And there's more, right? I mean, this R chart, X bar chart, P chart, these aren't the only kinds of control charts, but these are going to be the only kinds of control charts I'm going to do videos on that I'm going to show you, okay? And then just as with the run charts, right? When we're looking at a control chart, how do we determine if the process we're monitoring is stable or not? Well, same conditions really, right? Is there an obvious pattern? Is the variation seeming to increase, right? Does it start off as a low band and then the data values get further and further apart as you move forward through time? Is it obviously increasing? Is it trending upward? Is it obviously decreasing or trending downward? Is there that upward shift or downward shift? Is there an obvious cyclical pattern? Is there an exceptionally high or exceptionally low value? But now this time we have a way to determine that more easily, because we're going to have in these control charts these upper control limits and lower control limits. All right, so I've got just some of these conditions written out again here. So when we're interpreting control charts later, we're going to say that a process is not statistically stable or not in statistical control if one or more of the following out of control criteria are satisfied. All right, so again, this kind of sums up the 7 criteria that I had earlier, but there's kind of a new one here that relates to control charts and probabilities. One, if there's an obvious pattern, trend, or cycle, right? This kind of sums up a few of those earlier. Is there an upward trend, a downward trend, an upward shift, a downward shift, an obvious repeated pattern or obvious cycle, right? So this first one kind of sums up a bunch of the ones I had up earlier when we were talking about run charts. 2, if at least one point is above the upper control limit, right, the UCL, or below the lower control limit, right? So again, in the drawing, up here, down here, right, wherever these limits are. If there's a point above or a point below, something's up, right? Something's out of whack with our process, and we need to go in and fix it. It's out of control. All right, then this one's kind of new. Right? It still has something to do with obvious patterns, right? Still similar kind of to number one, but has a more probabilistic reasoning behind it. The run of 8 rule. If there are at least 8 consecutive points all above or all below the center line, right? Remember, the center line was this line at the average value, the mean value of all the data. So if these were all ranges, this would be the mean of all the ranges. If these were all x bars, if these were all sample means, this would be the mean of the means, right? And if these were all proportions, this center line would be the mean of the proportions. If you ever get a run that looked like this, where I had 8 consecutive points, if I ever had 8 consecutive points all above the center line, or 8 consecutive points all below the center line, like that, then there's definitely the probability of that occurring is very, very low, right? Because if you think about the middle being like a halfway point, think about the probability of being above the center line, and the probability of being below the center line is the same as about a half each. It's like flipping heads or tails. The probability of getting 8 heads in a row is incredibly slim. The probability of getting 8 tails in a row is incredibly slim. So the chances of that happening naturally are very slim. And we would not expect this to happen naturally. So if you see a run of 8 consecutive points above the center line or 8 consecutive points below the center line, we're going to determine that the process is not stable and go in and do something about it. All right. Now again, a little note here. I'm just going to base mine on these 3, right? And again, number one kind of ties into some of the earlier ones I mentioned when I was talking about run charts. But just a little note here: some companies use additional criteria to determine if a process is stable or not. All right, but I'm not going to get into that. All right, I'm just going to really stick to the ones I showed you earlier, along with this rule of 8, this run of 8 rule. All right. So again, no examples on control charts here. You're going to see I'm going to have one video each on R chart, X bar chart, and P chart. So hopefully after watching those, and I'll bring these pages back on control charts just to show you again when I make those videos. And hopefully the examples that follow will make a lot of sense. And I hope the example that was up earlier with this run chart made sense too, how I would look at a run chart like this and say, hey, no obvious pattern here, no extremely high, no extremely low values. Looks like the process of pressing lids onto these cans is working out for me. All right, it looks like it's stable. There's nothing I need to do to fix it. All right, so it's hopefully the way I interpreted this chart and other charts you'll probably look at. Hopefully listening to me interpret this one will help you in your interpretations of others. All right, so again, more control chart videos to come. Hopefully this introduction to statistical process control was informative, and enjoy practicing whatever problems you're going to be practicing of this nature. All right, thank you very much for watching.